Hello everyone, I hope you guys are doing very well. So here we have a grade 10 physical sciences paper 1 exam. If you would like to download the paper so that you can see what questions are going to be coming up, well then you can just check the description below and you can click the link and then you can have a look at the paper. Which of the following physical quantities is not a vector? Well, remember in grade 10 we've learnt about scalar, and we've learnt about vectors. Now, scalars, these things only have magnitude, which is like the size. So, for example, things like time. If you ask someone, hey, bro, what's the time? They're going to say something like 8:30. They're not going to say 8:30. Southwest. They're not going to give you direction as well. They're just going to give you the value. Okay, so time is a scalar. Some other scalars would be distance. What else? Speed. Temperature. If you ask someone, hey, what's the temperature? They're going to say 25 degrees Celsius. They're not going to say 25 degrees Celsius to the left. They're not going to do that, right? But when we look at now with vectors, they also have magnitude. They have magnitude, which is the same as like size, but they also have direction. Things like force. So for example, you might say, wow, bro, you pushed me so hard. That was like 10 newtons. But then you would have to say to the right, because vectors have a size, which is the 5 newtons. And let's actually write that down, 5 newtons to the right. So this part here is the magnitude, and then this part here is the direction. Okay, and so some other vectors that we've come across is acceleration, displacement, velocity, weight, whereas mass is a scalar. Okay, so it says, which of the following physical quantities is not a vector? Well, force is a vector, velocity is a vector, acceleration is a vector, so it's distance, and we can see we even said distance over here. So the first answer is A. In the equation delta x equals to that ugly thing, the part vi delta t represents the... Okay, now let me explain. We know that in grade 10 we've learnt about 4 of these equations, right? Our equations of motion, which we get on the formula sheet, as you can see over here. So the one that they've given us is this one over here. Okay, so just to show you that it's not something random, it's on our formula sheet. It's one of the equations of motion. Now, this part specifically over here, okay, remember from like earlier grades, maybe we started, I think probably around like grade 9, where we learnt about speed, distance, and time. Your teacher may have done it with a triangle. Not all teachers do it that way, but you may have seen this before, right? Where this is distance, this is speed, and this is time. And what we have learnt is that, for example, if you want to find distance, well, that is equal to these two multiplied together. So speed multiplied time. So let's just now switch all of that for the the vector values, which is, what is the vector of distance? Well, the vector of distance is displacement, and the vector of speed is velocity. Okay, now in symbols, displacement is often shown with an X, like that, and velocity is often with a V, and then time is often with a delta T, for example, something like that, okay? So have a look here, V multiplied by T. Let's just don't worry about that. Just say V multiplied by T for now. Can you see here we also have V multiplied by T? So that is displacement, because displacement is equal to velocity multiplied by time, and so the answer would be D. Not a nice question. I don't really like that one. In class, they don't really emphasize that part there is the displacement. I've never seen them do that. So this one may have caught you out. Don't worry if it did. It's not a common kind of question. You probably won't ever see this one, something like this again. Which of the following is obtained by calculating the gradient of a displacement versus time graph? Step 1, let's draw a displacement time graph. So displacement time. Okay, now whatever, doesn't really matter what it looks like. Let's just say it looks like that. Now we need to understand this idea of gradient. Let's go back to maths quickly. How do you calculate gradient? It's always the y over the x. What it actually means is the y-axis and the x-axis. So what is the y-axis in our example? Well, now it's displacement. And what is the x-axis? Time. Okay, so what would happen if you have displacement, the change in displacement, over the change in time? So you might even think of it as that. What is displacement over time? Well, that is velocity, right? Remember when we did our velocity time graphs or our displacement time graphs, whenever we calculated the gradient, that was velocity. Do you need more convincing? Well, remember from like grade 9, we typically started learning about distance, speed, and time. And from this triangle, if you had to calculate speed, that would be distance over time. Now let's convert these into vector values. So what is the vector of speed? Well, the vector of speed is velocity, and the vector of distance is displacement, and the vector of time, well, that just stays time. And so there we have it. Velocity is equal to delta x over delta t, which is what we have over here, and so it's velocity, b. In the diagram below, a pendulum bob of mass m is released from a point A and swings past point B, C, and D. Ignore all air resistance. In which of the following positions will the value of gravitational potential energy? Now, gravitational potential energy is EP. Remember? Energy potential. It's on the formula sheet, and it's mgh, where m is the mass, g is on Earth, 9 point, and h is height. Okay, so can we agree that at point A, B, C, and D, the mass of the object stays the same? So we're not even going to worry about that one. Can we agree that because we're on one planet over here, let's assume we're on Earth, it doesn't matter if this question's on Earth, Mars, whatever, the value of G, whatever it is going to remain a constant from here to here to here to here. So we don't even have to worry about that part. So the only part we really need to look at is height. So if this is our reference, let's say we've got the ground over here, then can we all agree that the largest height is this one and the smallest height is this one? So they said, where will the energy be the smallest? Well, that would be at C, because that's where the height is the smallest, and so this part here would have to be the smallest as well. The number of sound vibrations per second. Okay, so in grade 10 we started learning about waves, and with waves we learnt about things called frequency, and we learnt about the opposite of frequency, which is called period. Now with frequency, remember we said that it was the number of waves, or you could think of it as vibrations per second, whereas period was the opposite. It was the number of seconds per wave or vibration. So if they're saying the number of vibrations per second, then it's this one, frequency, which is B. Two identical spheres, A and B, on insulated stands carry different charges. The spheres are brought into contact and then separated again. If the charge on sphere A after the separation is Q, then the charge on sphere B would be, well, that would have to be this one, but let me explain. So what we've learned is that when you have two spheres, let's say this one's got a charge of, this one's very negative and this one's very positive. When you make them touch each other, right, then what happens? Well, electrons flow. They go from the one that's more negative to the one that's more positive. But let me explain that a bit more. We know that electrons are what? Are they positive or negative? Well, they're negative, right? So then if this one, so then which of these two has more electrons? Let's give them labels, A and B. Which one has more electrons? Well, that would have to be A, because A is negative and electrons are negative. So those electrons, they don't all like to be over here. Think about it. They, like for example, let's say you get onto how does it work in real life? If you get onto a bus, let's say you get onto a bus and there's people sitting in random seats, but there's a lot of open seats. As human beings, do we naturally go sit next to someone, or would you naturally go and find an unoccupied space where you've got a bit more space to sit? So think about that. Would you rather sit where there's empty space, or would you rather sit right next to someone if you had the choice? Well, naturally, you would go sit spaced out. And so that's what these electrons do. There's so many electrons over here. They're just getting a little bit annoyed because there's so many of them all stuck together. So they'll rather like to spread out, okay? So those electrons will naturally go over. Some of them will go over. And they'll keep doing that until we reach a situation where the amount of charge on both of these, A and B, becomes equal. At that moment, what would happen to A and B if they have the same charge all of a sudden? Well, what do we know about like charges? Like charges repel. And so all of a sudden, they're going to push each other away like that. And what happens is that because the electrons have moved over, some of them have moved over, they kept moving over until the charges on A and B is exactly the same. So if the charge on A is Q, then the charge on B is also Q. Don't say negative Q. The rule doesn't say that they're going to be opposite. No, they actually become exactly the same. So if this one is a Q, then the other one is also a Q. Consider, okay, now this part over here I've added by myself. Okay, this was not part of the question. Consider the circuit diagram below. What is the voltage across the parallel resistors? So remember, where is the parallel? Well, these ones over here are in parallel. So what we've learned is that the voltage of a battery, which is this part over here, is always going to be equal to the sum, which means plus, of all the voltages in series, which would be this one and this one. So what is the sum of those? Well, that's 1 plus 4, which is 5. So we can say that the voltage of the battery is 1 plus 4 plus the parallel branches. Okay, so let's just say here parallel branches. And we also know that the battery's voltage is 7. So now we can say 7 is equal to 1 plus 4, which is 5, plus the parallel. So if you had to calculate the parallel, you would take the 5 to the left, and you'd end up with 7 minus 5, which is 2. And so the parallel is 2 volts. What that means is that this one is going to be 2 volts, this one is 2 volts, and this one is 2 volts. Remember, we've spoken about this. We've said that you mustn't take that answer that you just got and divide it by 3 or anything like that. No, we've learned that in parallel, they're all going to be 2 volts, which is quite interesting, right? But we have looked at that in previous lessons. Which of the following statements best describes resistance in parallel? Now, we've spoken about this before, but let's talk about it. So, remember that, let's say we've got a whole bunch of people, okay? And those people are walking over here. Let's say we've got 10 people. Now, let's say they need to walk into the shop. The shop is over here. Okay, so here's a shop. Now, to get into a shop, there's doors. So, let's say this shop is really weird. They've got a door over here. That's door 1. Then they've got another door over here, door 2. And then they've got another door over here, door 3. Or let's make it the final door, which is like entering the shop. So to go to the shop, you have to walk through all 3 doors, one after each other. Okay? Do you think that's going to make it really easy for people to move in and out when you have to go through all 3 doors like that? Or do you think it's going to be a bit silly? Like, literally think about that. Let's say you're walking into a shop, like, I don't know, Pick n Pay, Checkers, Spar, whatever. Just think of any shop, okay? And you have to open a door, then close a door, go through, next one, open, close, next one, open, close. That's going to be terrible, right? Wouldn't you say that it's going to make it's going to make the speed or the flow of people really slow because they got to constantly open doors, close doors, open doors, close doors. What we will say here is that the resistance Think about the word resistance. If something resists you, it means that it's trying to stop you, right? Resistance, it's resisting, it's trying to stop you. So the resistance here would actually be very high. Can we agree that it's going to be very difficult for these people to move? It's going to be very slow. It's going to be annoying. It's not going to be a great experience. Now, what if we rather design the shop in a little bit of a different way, where instead of making the people go through like that, we rather do the following. Let's redesign this shop. Okay, so obviously we have the same shop. But now instead of doing it like that, let's rather make these people go through, or we'll offer a door here, which we'll call door 1. Then we'll have a door 2, and then a door 3. Now to enter the shop, you can either go that way, or you can go that way, or you can go that way. Is this going to make things better or worse? Well, if you understand this correctly, this is going to make things 100 times better, because now when each person gets over here, they can decide to go that way, or that way. They only have to go through one door instead of going through all 3 doors. And so would we agree that it's going to allow the flow of people to go through a lot faster, smoother? So what we'd say here is that the resistance, the overall resistance is actually going to become low. Now, this is exactly how it works in electrical circuits, where the people are electrons and the doors are resistors. So when you add more resistors in parallel, remember these are parallel to each other, whereas if you add the doors like this, that's called series, because you have to go through every single one. That is series, whereas this is what you call parallel. So when you add more doors or more resistors in parallel, the overall resistance in the circuit actually becomes less. Let me prove this to you mathematically now. Check this out. It's quite interesting. It's really cool. Because if you don't think about it properly, you'd naturally think that the more resistors you have, the higher the resistance. But that's only if you do it in series. Check this out. Let's say we have 2 resistors, a 2 ohm and a 4 ohm. Now, because they connected in series like this, what is the overall resistance? The overall would be 2 plus 4, which is 6. If you then add another door, so let's add another door, 4 ohm, let's add a 5 ohm, then what is the overall resistance now? Well, it just goes even larger, 2 plus 4 plus 5, which is now 11. So you see that's in series. This is in series. Let's do the same thing in parallel. So in parallel, if you have a 2 and you have a 4, then what's the overall resistance? Don't say 2 plus 4. Remember that when you are in parallel, you got to use the parallel formula, which goes like this. 1 over 2, 1 over 4. Now, if you had to go add this all up, you end up with 3 over 4. And then you have to flip this and flip this around. So R parallel becomes 4 over 3, which is the same as 1,33 ohms. Now, I'm going to add another one in parallel. So let's say, for example, I now add another one over here, which is a 5 ohm. So then when you calculate this part, you're going to say 1 over 2, 1 over 4, plus 1 over 5. Now, if you had to go add all of that together, you end up with 19 over 20. So we could say 1 over R parallel. So then 1 over R parallel is 19 over 20. So let's just write it over here. Now, to get R parallel, you have to flip that over, which is now 20 over 19, which is 1.05, which is less than this. So can you see that when you are in series, when you add more, what happens to the overall resistance? It goes up. But when you are in parallel, when you add more, the total resistance actually goes down. Check this. It was 1.33 when we only had 2 resistors. Then we added a 3rd resistor, and all of a sudden it's gone down to 1.05. And if you just had to keep adding more resistors in parallel, the overall resistance actually becomes less because you're making more pathways available for the electrons, just like we're making more pathways available for the doors, for the people with the doors, and so the overall resistance actually becomes less. So it's this answer. Adding more resistors in parallel decreases the effective resistance of the circuit. That's the same as saying adding more doors at a shop in parallel allows the people to move through the shop or enter and exit the shop more easily. Okay. This question starts by asking us to define the term vector. Now remember, we've got two things from grade 10. We've learnt about scalars and we've learnt about vectors. Now, scalars only have magnitude, which is size. For example, if someone asks you what's the time, you're going to say 8:30. You're not going to say 8:30 south. That would be a bit weird, right? So you only give the value. If someone asks you what's the temperature, you would say it's 12 degrees Celsius, but you won't say 12 degrees Celsius to the left. So you see how you only give the magnitude. But when you're looking at vectors, then you have you have magnitude, which is the size, but you also have direction. For example, if we're talking about force, then you would say 5 newtons left, or 5 newtons up, or 5 newtons south, for example. So with vectors, you tell them what the value is, but then you also give a direction. So what is a vector? It is a physical quantity having both magnitude and direction. This question says, Peter stands at the front door of his house. Okay, pretty creepy drawing over there, I won't lie. Going to be traumatized. Peter stands at the front door of his house. Avogadro Street is 25 meters away. Okay, we can see that over there. Peter walks to Avogadro Street, like a little creeper, walks to Avogadro Street, and then randomly walks back to his house. What a weirdo. Okay, now it says, what is the distance? Now, distance is very easy. You've been using distance since you were like 3 years old. Like, it's super easy. If you walk 10 meters and you walk another 10 meters, then how far have you walked? 20 meters. So if you walk 25 meters that way, and then you walk 25 meters that way, well, that's easy. That's just going to be 50 meters. But in the next question, they say, what is Peter's displacement? Now, here's where things get interesting. We've learned that displacement, you have to be careful. You must look at the starting position. So where was the starting position? Well, the starting position is Peter's house. Where's the ending position? It's not here, by the way. It is also over here. Why? Because Peter walks to Avogadro Street and then walks back to his house. So the starting and the ending position are both at Peter's house. So what is the distance between the starting and the ending position? 0 meters. Because you're starting and you're ending at the same place. So the displacement is 0. The next question. Is displacement a vector or a scalar? Well, we need to know that that is a vector. Why? Because it has magnitude, and it has direction. So some of you are like, but Kev, why didn't we give a direction over here? Well, we normally would, but you can't when it's a 0. You can't say 0 meters right, because then it means he went right for the displacement. But he didn't. He didn't go anywhere with the displacement. Guys, with this question, 3.4 has a mistake. We'll obviously get to that, but for those of you that maybe wanted to go ahead and try it without me, what you'll notice is that they've given us too much information. So they've given us the distance, they've given us the time, and so you could actually use any of these formulas, well, except for, you'll notice that you can't use this one, but you could use any of these formulas, and what you're going to notice is that you're going to get a different answer for each one. Okay, so that's just for those of you that are wanting to work ahead. They've given us too much information for that question, so you get different answers. It's called, I like to call it over-specified. They've given too much. They've over-specified the question. Okay, but for those of you that just want to go through this with me, let's begin. Car A driving at 135 kilometers per hour. That is really fast. Okay, this guy's speeding. You're not allowed to go more than 120 on the national roads of South Africa. So this person is speeding. So approaches a stationary car, meaning this car is not moving. Okay. The driver of car B notices that car A is approaching him at a very high speed. The driver of car B reacted suddenly by accelerating his car from rest at 1.5 meters per second to the -2 for 11.5 seconds. So we've got this car that's speeding towards car B. Car B gets a fright and decides to start driving off to hopefully try get away from this car. After 11.5 seconds, car B continues driving with a constant velocity. First question, convert this to this. Okay, so whenever we're going from kilometers per hour to meters per second, you need to divide by 3.6. And if you are going from meters per second to kilometers per hour, then you will multiply by 3.6. You just have to remember that magic number, 3.6. Teachers aren't going to see where, they're not going to expect you to show where you got the 3.6. They might show it to you in class, but in an exam, you can just say 3.6. Okay, so we are literally just going to say, we're going from kilometers to meters per second, so we're going to say 135 divide by 3.6, and that'll give us 37.5, and now that is in meters per second. This question, determine the velocity of car B while trying to avoid car A. All right, so we know that car B starts at 0, so that's its initial velocity. We know that it has an acceleration of 1.5, and we know that it's going to drive for 11.5 seconds. So now we've got to try to see which equation of motion would be best. So we have the initial velocity, we have the acceleration, and we have the time. So we could just use this formula, but you could use others. You could probably, oh no, we don't actually know we don't know the displacement. Okay, yeah, so this would be the best formula. So always write the formula down. They'll usually give you 1 mark for that. So VF equals to VI plus A delta T. Now we can go fill everything in. So the initial velocity is 0, the acceleration is 1.5, and the time is 11.5. If we work that out, we get 17.25 meters per second. So 17.25 meters per second. This question says, how far did car B drive in 11.5 seconds? Well, I would go straight to this formula, but, or no, you could use any of them, to be honest. You could use this one, you could use this one, or you could use this one. I'm actually going to go with this one, just nice and easy, gives us the displacement straight away. So we could just say, always write down your formula. So delta x equals to VF plus VI over 2 times delta t. Right, so delta x is equal to, now the final velocity for car B we said was 17.25. The initial velocity is 0, and then the time is 11.5. So if we had to work that out, we get 99.19 meters. So 99.19 meters. Now, here's the question that I mentioned has got a bit of a mistake because they've given us too much information. So you could use different formulas, and unfortunately, you're going to get different answers for each of them. Okay? So I'm going to just choose one of the formulas. So I'm just going to choose the most straightforward formula, which will just be this one over here. So what do they want us to calculate? What acceleration? Okay, so they want us to calculate A. Now this is for car A. So we know that car A initially, in the beginning, was traveling at 37.5. You might say the 135, but we must always do it in meters per second. And then we know that it comes to a stop. We know that it comes to a stop because it says here, and manages to stop. And we know that the time to do that is 4 seconds. For them to have made this question correct, they shouldn't have told us, they should have taken either that part out, or that part out, or that part out. But they gave us everything, and that's too much information, okay? I'm quite surprised that they managed to make that mistake, because it's quite a rookie error, to be honest, if you're like a teacher who does the stuff for a living. So VF equals to VI plus A delta T. Now, the final velocity is 0. The initial velocity is 37.5. And then the acceleration is what we're trying to calculate. And the time is 4. So this just becomes 4A. Don't put all of that together. A lot of students do that, but you can't because this one doesn't have an A. So you're going to end up with 37.5 plus 4A. And then take the 37.5 to the other side. And then divide both sides by 4. And so A, if you use this formula, would be a negative value. And it would be negative 9.38. Oh, but I need to 9.38 meters per second to the negative 2. Now, for those of you that maybe did use other formulas, I know that if you used this formula, you would get an answer of negative 13.75. And if you used this one, let me just quickly work this out for you. Just hold on. Ba-da-bum, 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 dum, boom. Yeah. If you use this one, you would get negative 17.58. Okay. So sorry about that. Yeah, it's not my fault, but different answers depending on the formula. So that is not supposed to happen. You can't have a situation in life where the formulas give you different answers. They gave us too much info there. Study the velocity versus time graph below for the motion of a car traveling east. Okay, so we've looked at velocity time graphs before. So here's velocity and here's time. The first question, define the term acceleration. Well, remember, acceleration, when I've showed you the formula for acceleration in our lessons, we went like this. So it's the change in the velocity over the change in time. So the way that you would write that is, it is the rate. Whenever we talk about time, we say rate of change of velocity. So it is the rate at which the velocity changes. That's what time is. So rate of change of velocity. Use the graph to describe the motion of the car in the following sections. Okay, the first section that they would like us to look at is AB. So from A to B. Okay, so if you look at the velocity at A, it's 0. If you look at the velocity at B, if you read its velocity, it's 10. And if you look at the time, it's 20. So what we can say is that the car accelerated from 0 meters per second to 10 meters per second in 20 seconds. The next question says, use the graph to describe the motion between CD. Now, some learners, they will immediately say, oh, Kev, the object's not moving, hey? That's not true. You got to be careful. If it was a displacement time graph, then you would be correct. But it's a velocity graph. So think about this carefully. At point C, the object is moving at 40 meters per second. So it's definitely moving. At point D, ooh, it's also 40. That means the object is moving between C and D. But the velocity is not changing. So we can just say that the object, or the car, is moving at a constant velocity. Moving at a constant velocity. And then EF, what is the velocity doing at EF? Well, now we can say the car is not moving. Why? Well, if you look carefully, at E, what's the velocity? 0. At F, what's the velocity? 0. So the object is not moving. So we can say the car is not moving. This question over here says, calculate the acceleration between D and E. Now, remember, acceleration is this. So all that you do, okay, is you got to think about this. Is D the initial or is E the initial? Well, so remember that the initial is the start and the final is the end. So if you look at these two, which one's the end and which one's the start? Well, look at the time. This one's time is at 50. This one's time is at 60. So what comes first? Well, 50 comes before 60. So this is the start. And this is the end. Well, this is the end. So that means that this is the final position. So we'll get our final values over there. And then this is the starting position. So we will get our starting values over there. So now we just use the formula. So the first the value is the final velocity. So we go to the E because that's the final. And to read off the velocity, you go to the y-axis, which is the velocity. And what is it? It's 0. So we say 0. Then we say minus. Now we need to go to the initial velocity, which is at the initial position. So that's here. So to read off the velocity, you go to the y-axis, which is a 40. Now to find the final time, we go to the E, and now we read the x-axis, which is time. So that's going to go down to, that's 60 over there. And then you go to this point over here. But now to find the time, you don't go this way because that's velocity. You rather go to the x-axis because that is time. So you go down, 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 down. And so what is it? It's 50. And so if you had to calculate this, you should eventually end up with -4 meters per second to the -2. But now they told us in the beginning that the car was originally moving east, right? And all of these are positive values, so the car was definitely going east. And so what we now do is we don't leave this with a negative. We then say, therefore, the answer will be 4 meters per second. So because east is positive, but we got a negative answer, you're going to say west. Okay, because that's the opposite of east. And then this question here says that in which section AB, so this part here, or BC, is the acceleration the greatest? Well, this is an easy one. Let me explain. We know that acceleration is change in velocity over change in time. Now, for some learners, you might also remember, or you might also understand, that acceleration is the gradient of the velocity time graph. So then immediately, and I will explain this in a different way shortly, but immediately you would know that the answer is BC because it's got the steepest gradient. And if acceleration is the gradient, then this part here would have the greatest acceleration because it's got the steepest gradient. But let's prove that now using calculations. So once again, we know that acceleration is this, right? So if we look at AB, section AB, so from here to here, then this is your final, and this part here is your initial. So if we had to work this out, your final velocity is 10. Your initial, what is your initial velocity? Well, that's this one, so that would be 0. Then your final time is 20. And your initial time is 0. And so if you had to work this out, you would end up with 0.5 meters per second. Now, if we had to go do the same thing for BC, then all of a sudden, B is now your initial position, and C is now your final position, because that comes later. And so your final velocity is then going to be 40. Your initial velocity is then going to be 10. And then your final time is 30. And your initial time is 20. And so if you had to go work this out, you're going to end up with 3 meters per second. And so can you see that at BC, the acceleration is larger than at AB? So the answer is definitely going to be BC. And we can just say the gradient is the steepest. So just remember that. Oh, I'm writing really ugly. So just remember that gradient, the gradient of a velocity time graph is the acceleration. A roller coaster of mass 2 kilograms is released from point A, which is 30 meters above the ground. We can see over here that they've said 30 meters, and then the cart moves along a frictionless surface. Only in grade 12 will we actually start adding friction for these kinds of questions. ABC as shown below. The first question says, define the term gravitational potential energy. So before we give the definition, do we know the formula for potential energy? Well, potential energy on our formula sheet is mgh, where m stands for the mass, g on planet Earth would be 9.8, and h is height. So the definition is the energy of an object due to its position, or you could even say height, above the ground. Okay, this one. Prove with calculations that the mechanical energy. What is mechanical energy? Mechanical energy is, so remember, so in grade 10, and we're going to look at this again in grade 12. In grade 11, we don't really, but in grade 10 and grade 12, we're going to look at mechanical energy. So we've learned that mechanical energy, well, let's quickly talk about, we have two types of energy that we study in grade 10. One of them is energy due to height, and that's the one we just looked at. That is called potential energy. Okay, so we call that one, or I'll just say potential energy, EP, energy potential. Then we get another type of energy in grade 10, which is energy due to how fast an object is moving. An object is moving, and that is called kinetic energy. Kinetic energy. Now, if you take those two energies and you add them together, that is called mechanical. So it says, prove with calculations that the mechanical energy at point A is 588. So is the object moving over there? Let's just see. The roller coaster is released from rest. Okay, so not moving. So that means, okay, so normally you would have to say that the mechanical energy is kinetic plus potential. But because the object is not moving, the kinetic energy will be 0, because kinetic energy is a half mv squared. And if the v is 0, so we could even say that, because we know that kinetic energy is a half mv squared, and we know that potential energy is mgh. So we could say a half times the mass. What's the mass? 2. What's the velocity? 0. Plus, what's the mass? 2. What's gravity? 9.8. What's the height? 30. You see, I'm just using this formula, and then for the kinetic energy, I used its formula, and for the potential energy, I used its formula. And so if you go work this out, you end up with 588 joules. Okay, now moving on to question 5.3, it says state the law of conservation of mechanical energy. Now let me first explain that. So we've said that in grade 10 we've got two types of energy. We've got potential, which is, you can think of it as due to the height, and then we've got kinetic, which is due to how fast. Okay, and then when you plus them together, that gives you mechanical. So when this object is over here, we said that because it's not moving, it only has potential energy. How much mechanical energy does it have altogether? Well, it had 0 over here and it had 588 over here, and so we found out that the total was 588. Now that 588 will not change at all. The mechanical energy will stay 588. But what will happen is the following. As this object begins to go down the slope, what will happen to this one? Well, can we agree that its velocity is going to start going up? You can think of it as its speed. It's going to start going faster and faster. So that means your kinetic energy will go up. But at the same time, as the object is going down the slope, what will happen to its height above the ground? Well, that'll become less. And so what will happen to this energy? Well, that'll go down. So this one goes up, this one goes down, but guess what? The total will be will always be 588. Only in grade 12 will that maybe start changing when we start using friction but we said it's frictionless. So when there's no friction around, the mechanical energy of an object does not change. Yes, the potential energy can go up and down, and yes, the kinetic energy can go up and down. But if you look at the total, the mechanical energy, that never changes. So that means the mechanical energy at point A is 588. The mechanical energy at point B will also be 588. Obviously, it'll have a different kinetic and potential value, but the total will still be 588. And then at point C, same thing, 588 for the mechanical, but maybe the potential will be different and the kinetic will be different. But if you add them together, it'll always be 588. Now, your teacher might give a slightly different definition, but pretty much the law of conservation. What does conservation mean? It means that you are protecting something, or something is not changing. There's different ways of looking at the word conservation, but it means that you're trying to keep it the same. And so mechanical energy stays the same, right? We said it's 588 in this particular question. So what we can say is that the mechanical energy of an object in an isolated system. Isolated just means that if something's isolated, it means that it's shut off from the rest of the world. What they mean is, if you're just looking at this little box system over here, and you don't have any other things coming in, like friction, you don't have any of that coming inside. We're just pretending that it's a nice, perfect little world where there's no things like friction, air resistance, all of that. Then we say that the mechanical energy of an object in an isolated system is conserved, meaning it stays the same. This question, calculate the velocity at point B. Now check how easy this is, okay? Have a look at this. What we have said is that the mechanical energy never changes. So what is the mechanical energy at B? Well, there we go, 588. We know that. So we can say that the mechanical energy at B is 588. We don't even have to go do a calculation for that, because we know that mechanical energy stays the same everywhere for this object. Now we know that mechanical energy at B is going to be the potential energy at B plus the kinetic energy at B. Right? Because that's what mechanical energy is. So we can go fill in the formulas now. We know that this one is mgh, and this one is half mv squared. Those formulas are given to you on your formula sheet. And so what we can fill in here is 588, because we know that that's what the mechanical energy is. We know the mass of the object is 2. We know gravity is 9.8. We have the height over there as 10. We know the mass of the object once again is 2. We don't know the velocity. That's what we're trying to calculate, like that. And so you can go and type this on your calculator, and you get 196. So we can say 588 equals to 196 plus. Now this you can type on your calculator, just this part here, half multiplied by 2, that's 1. And so 1, I don't need to put a 1 there, because if there's a 1 there, then it doesn't, you can just leave it out. We know that there's a 1 there. So now we just solve. So we take the 196 to the left. So we say 588 minus 196, and that'll give us 392 equals to the velocity of B squared. And then to get velocity of B by itself, you take the square root of 392. And so the velocity of B will be 19. If you round to 2 decimal places, it'll be 19.80 meters per second. And then this last one says, how will the mechanical energy of the cart at point C compare with the mechanical energy at point B? It will be exactly the same. So we're going to say here same. Or so they said equal to. So we're going to say equal to. And then just say mechanical energy is conserved. Mechanical energy is conserved. Remember, guys, in grade 10, mechanical energy does not change no matter where the object is. All that happens is the potential energy changes and the kinetic energy changes. For example, I told you that as you go down here, what will happen to the potential? it'll become less because your height is decreasing. But what will happen to your kinetic? It'll go up because you're speeding up. But then when you go from B to C, well, now all of a sudden the object's going uphill. So what would happen to its potential energy? Well, that will begin to increase again because the height is increasing. But what will happen to the speed? Well, if you're going up a hill, your object is going to start slowing down. So your potential energy would go up, but your kinetic energy would go down. But guess what? Your total will always be 588. The diagram represents the pattern of waves that have a frequency of 30. What is frequency, guys? Can we remember? Well, frequency is number of waves per second. Remember that. So that means that in 1 second, think about this, in 1 second, there will be 30 waves. And a wave goes the up and the down part. That is a wave. So in this question, there are actually 2 waves that we can see. Here's the second one. Okay. So frequency means number of waves per second. So in 1 second, if you were standing over here, you would see 30 of those waves coming past. So they're moving quite quick. First question, define the term transverse. Before we define, let's understand it. So in grade 10, we've learned about 2 types of waves, right? We've learned about transverse and we've learned about longitudinal. With transverse, this was like when I explained it like the Mexican wave when you're at a sports ground. When you're at a sports stadium and you've got a Mexican wave, if you've been part of that, you know that the wave moves round and round and round. But what are the people doing? The people are not moving round and round and round. They're moving up and down. So the transverse wave was the one where the particles go up and down, for example, but the wave went left or right. Okay? So if the wave goes this way and the particles go this way, there was a 90 degree. Remember, let me draw that a bit better. There was the 90 degree between them. So the transverse wave is when the particle moves at perpendicularly to the direction of the wave. So the definition is a wave where particles in the medium move perpendicularly to the direction of propagation of the wave. So we're just saying that it's where the particles move perpendicular to the direction of the wave. Okay, now it says label points A, B, and C. So we know that A is the bottom and C is the top. So let's just say when life gets tough, you feel like you're in the trough. Never actually used that before. So A is going to be a trough. And then the other one, which is the one at the top, is the crest. When life gets tough, you feel like you're in the... Sorry, when life gets rough, you feel like you're in a trough. Or you can say tough, rough, trough, whatever. It will all help, right? And then B, well, you see, B is going from the same position to the same kind of position. We call that a wave length. So B is the wave length. This question, how much time has elapsed while the wave moved from R to T? Okay, so can you see that R to T is one wave? So let's think about this. We know that the frequency is 30 waves per second. So think about that. In 1 second, there are 30 waves coming past. But what we want to know is how long does it take for one wave? Because if you go from R to T, that is one wave. That is only one wave. So remember that frequency is equal to 1 over period, and period is equal to 1 over frequency. Well, what we need to calculate is the period, which is the number of seconds for one wave. And so we can say T is equal to 1 over 30. And so if you work that out, you'll get 0.03 seconds. This question says, are the points R and S on the wave in phase? Well, no, they're not, but let me explain. Remember, we've spoken about this before. If you look carefully, R, if you look at the line going to the right of point R, it's going up. If you look at the line to the right of point S, it's going down. So they're not in the same kind of position. But if you had to look at R and T, so look at R and T. So with R, it's about to the line's about to go up, and if you look at T on the right, it's about to go up. If you look at U, it's about to go down. If you look at this, okay, we're not going to look at that one. So you can see that these two are in the same phase, and this one here is about to go down. So these two are also in the same phase. These two. And so remember that for 2 points to be in phase, they have to be separated by a certain number of wavelengths. For example, from R to T, how many wavelengths is that? That's 1. But if you go from R to S, that's not even a wavelength. If you go from S to U, that is a wavelength. Check, it goes down and then up. As long as it can go down and up or up and down, that's a wavelength. What about, let's say we made this called V. Then check here. 1, 2. So as long as it's a certain number of wavelengths, then they are in phase. But if you look at R and S, that's like a quarter of a wavelength. So we will say no. Let's say R and S are not separated by a whole number of wavelengths. Like, it's not a whole number, it's a quarter. Okay, and then this question says calculate the speed of the wave. Now, we've looked at waves and we found different formulas for speed. One of them is this formula over here, and that's probably the one we're going to use. But then also keep in mind that for waves, we don't really use it, but sometimes they'll also ask you to use distance over, sometimes you could also use distance over time. But they haven't really spoken about time in this question, but we have spoken about frequency and then wavelength. Remember that this is wavelength. So we already know the frequency. The frequency is 30. They gave that to us. And the wavelength is the distance of one wave. Now, they haven't given us that one, but that's okay because they've given us this one. As long as it goes from a place that's the same to another place that's the same, that is a wavelength. That is one wavelength. Okay? And so that is 4 meters. So we're just going to say multiply by 4, and that's going to give us 120. Now, what are the units of velocity or speed? Meters per second. So m dot s minus 1. 2 identical insulated spheres, A and B, suspended by a light string from a ceiling, are held a distance apart as shown below. Sphere A carries a charge of 2 nanocoulombs, whereas sphere B is neutral. First question, what is meant by neutral? Well, we know that if we have to look at an atom, okay, so we go down to the basics of an atom. In the center of an atom, we have a nucleus. Okay, so this would be your nucleus. Let's write this a bit better. Inside the nucleus, you've got 2 kinds of things. You've got neutrons and protons. Okay, so you've got some positive things, which are called protons, and you've got things that don't have any charge, and they are called neutrons. And then on the outside of the nucleus, in these little energy levels, we have things called, well, things that are negative, and they are called electrons. Now, electrons are negative, and protons are positive. So when you have the same amount of electrons and protons in an atom, then the overall charge is 0. Let's say, for example, you have 5 negative electrons and 5 positive protons. Well, if you look at the overall charge there, that would give you 0. So a neutral charge is an atom with an equal number of protons and electrons. It's got nothing to do with neutrons. Okay, let's move on. Sphere A is brought near the sphere B, and the spheres are allowed to touch. Immediately after touching, sphere B moves away. Sphere B now has an excess of 20 electrons. Okay, so let's talk a little bit about that. Okay, so let's say we have two charges, C and D. Let's make this one positive, and let's make this one negative. Now, what we've learned is that this one is negative because it's got more electrons than protons, and this one is positive because it's got more protons than electrons. So if you then had to make these two spheres touch each other, so like the C over there, D over there, then electrons will always go from the negative one, and they will start moving over to the more positive one. Okay? And that will keep happening. So as the electrons go away from this one over here will start becoming a little bit more positive because it's losing all the negative electrons. And then this one will end up becoming less positive because it's now gaining electrons. You see, so there's a balancing effect that's happening. So all the negative electrons on D, or not all of them, but a lot of them, are going to move over from D to C until we reach a point where the total charge in C is going to be exactly the same as the total charge in D. At that point, they have exactly the same charge, and so what would happen? Well, they would shoot away from each other because charges that are exactly the same repel. And so they would then move away from each other very quickly, but they would have exactly the same charge. So if this one was Q, then this one would also be Q. They would have exactly the same charge at that point. So now we can start the questions. So this question says, state the principle of conservation of charge. Well, before we go get the definition or the principle, let's just talk about this a little bit. If you had to draw a big box around this over here, let's say that there were, for example, 20 protons and 30 electrons and 10 neutrons. I'm just making up some random numbers now. If you're to then draw that big box around this one, these numbers would be exactly the same. And if you had to draw a big box around this one, those numbers would be exactly the same. All that's happening is that electrons are just going to move from this one to this one. So, but the total amount of everything stays exactly the same. What I'm trying to say is that there isn't like some new electrons or protons or neutrons that somehow enter into the system. No, all the protons, electrons, and neutrons that we have, if you add it all up together for both of those, that number will stay the same. All that will happen is that at the end, this one will have less electrons than it started with, but this one will have more. But the amount of the protons, electrons, and neutrons, if you add it up for both of them all together, that doesn't change. So what we can say is that charge is conserved. So your teacher might use a slightly different one, but on this memo, they said that the net charge, what that means, the overall charge of an isolated system remains constant during any physical process. So what they're saying here is that if you had to look at all the protons, electrons, and neutrons for C and D all together, when you look at the total amount of electrons, protons, and neutrons all together after the process has taken place, after we've made them touch and they've moved away, it'll still be exactly the same. Yes, this one will now have less electrons, but this one will just have more electrons. So it all balances out. The electrons that this one loses will be the same as the electrons that this one gains. So if you had to look at all the electrons overall, that won't change, right? If this one maybe had, let's say for example, this one in the beginning had, whoopsie, let's say this one maybe had 20 electrons, and this one over here had 10 electrons. Then how many electrons do we have altogether? 30. So then maybe afterwards, this one would now have 15, and this one would now have 15. So can you see we still have 30 electrons? That doesn't change. That's what we're trying to say. We're trying to say that the overall charge doesn't change. All that happens is you're moving electrons from one to the other. This question says, briefly explain how the neutral sphere B is attracted to sphere A. Okay, so you see what they said here? They said that sphere A is brought near B. So what they do is they push A towards B. Now, as that happens, you see that A is positive, right? So all of the things that are in here that are positive are going to run away. Why? Like charges repel. So all of the positive protons are going to end up moving to this part of the molecule or atom to try get as far away from the positives inside here. At the same time, all of the negatives inside here are going to go collect on the left-hand side because they are attracted to the positive. Opposites attract. And so what we have now developed due to a process called polarization is we now have an atom or a sphere that has negatives on the one side and positives on this side. And so now these negatives will be very attracted to this one. And so these two spheres can now be attracted to each other. So we can say here, due to polarization, and the word polarization is actually a really easy one to understand. You know how we have the Earth? You've got the North Pole, and South Pole. So we've got two different areas. So we call them poles. So here we've got a negative pole and a positive pole. So we've got two different poles. So we just call this process polarization or polarization. So due to polarization, electrons in B will collect on the side closest to A, whereas the protons in B will gather on the side, let's rather write this over here, on the side furthest from A. We can then say a negative charge is produced. Or actually we could have said, a better way we could have done this is we could have said, due to polarization, electrons in B will collect on the side closest to A. Then over here, you should have said producing a negative charge, and then whereas the protons in B on the side, whereas the protons in B will gather on the side furthest from A, producing a positive charge. Okay, so over here, you should have also said producing a negative charge. Okay, and then let's move on. So calculate, for 3 marks, calculate the magnitude of the charge of sphere B. This is, here we go. This is after they've touched. And it says here that sphere B now has an excess of 20 electrons. Let's talk about that a little bit. When we say that a charge has an excess, what does that mean? Well, if we say that something has an excess of 20 electrons, excess means it's like, how do I explain? It has an excess. Excess means like more than. So, or it's got extra electrons. So it has an excess. So what it means is that B has 20 more electrons than protons. So what would its overall charge be? Positive or negative? Well, electrons are negative, protons are positive. If you've got an equal amount of them, then your overall charge would be neutral. But if you have more electrons, then your overall charge would be negative. So they're telling us that it has 20 more electrons. So we could then work out its overall charge, because we know that the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. That is given to you on the formula sheet. So if then there's this other formula. Let me go grab it for you. It's also on the formula sheet. So it's this formula over here, where N is number of electrons. E, sometimes they say QE, sometimes they just say E. It's the charge of one electron, which is this value that I gave you down here. So we'll just say E. And then Q is the overall charge. So it says, and that's what they're asking us to calculate. So we can say N equals to Q over E. The number of electrons they told us is 20. The Q we don't know. And then E is negative 1.6 times 10 to the negative 19. Now remember, to get this one by itself, you're going to take this value and you're going to multiply it up over there. And so you're going to end up with Q being equal to 20 multiplied by negative 1.6 times 10 to the negative 19. And if you work that out, you end up with negative 3.2 times 10 to the negative 18 coulombs. Okay, now this question, last one, says calculate the charge on each sphere after they have separated. So there's a formula for this as well. Remember that they took this one and they took this one, they put them closer together, they made them touch, and then they move apart again. There is a formula that we can use to calculate what each of their charges will be after they have moved apart. There's actually a big problem with this question. It's not correct. That's quite a big mistake that they've made. So we know that there's, let me go get that formula first. So there's this formula over here. Now, sometimes I use the word Q nu. So this formula helps us to calculate the charge of each of them after they've touched. So the way that you do it is you take the charges before they touch, which is these ones over here. So it's going to be 2 nanocoulombs. So you would always want these two to be in the same units. But yeah, so we can leave it as 2. Just remember that's nanocoulombs. Neutral means 0. Divided by 2. And if you work that out, you end up with 1 nanocoulomb. So that means that each of these will be 1 nanocoulomb, and that would actually be your answer. However, so this is actually the correct way. This is what I say the answer must be, and trust me, it is perfectly correct. This part here is completely wrong. They just made up some random nonsense over here. This is completely wrong. Because for those of you that understand this section quite well, you might have thought from 7.4 that where we got an answer of 3.2 times 10 to the negative 18, what was that? That was the charge of B after they touch, because it said immediately after touching, sphere B moves away, and sphere B now has that. So that means sphere B has this charge over here. So technically, if that's the charge of sphere B, then that would also be the charge of sphere A, because we've learned that when they move apart from each other, they always have the same charge. But, so this part here doesn't make any sense. They shouldn't have added that at all, okay? So don't worry, everything we've done so far is correct, but now 7.5 doesn't make sense. So the correct way you would have done 7.5 is to do it like this, okay? You just take the two charges. You take the two charges before they touch and you work out what they will be after they touch. The reason I'm saying there's a mistake is because this is the charge that we're getting for A and B after they touch. But if you use 7.4's answer, that is what the charge of B was after they touch. And so can you see that these two are not the same? And that's where they've made a mistake. In the circuit diagram below, each cell has a voltage of 1.5. Okay, now remember, a cell is a long line and a small line. So there's how many of those? There's one there, there's a second one, there's a third one, there's a fourth one, and there's a fifth one. Okay, so that means there's 5 of them. So what is 5 multiplied by 1.5? Well, that'll give you 7.5 volts. So this is a 7.5 volt battery. So it says, what is the reading on V1? Well, there we have it, 7.5 volts. This first question here says, calculate the following: the total resistance of the circuit. Well, that's easy. You've got to look at all the parallel parts and all the parts in series. So here we have a parallel part. So let's go add that all together. So you use the parallel formula, remember? So you say 1 over 6, 1 over 4, plus 1 over 3. So if you then go type that all in, 1 over 6 plus 1 over 4 plus 1 over 3, you end up with 3 over 4. And then you have to flip both sides upside down. So R parallel is equal to 4 over 3 ohms. And now we've got all of that combined. And now we just add that with this one, okay? And so 4 over 3 plus 2.67 will give you exactly 4 ohms. This question says, what is the reading on A1? Okay, so we know that to calculate current, we use I equals to V over R. Now, if we use the total voltage in the circuit, so let's use the total voltage in the circuit, which is 7.5, then you have to use the total resistance in the circuit, which luckily we've just calculated was 4. And so if we round that to 2 decimal places, that'll be about 1.88 amps. Okay, and then this question says, what is the reading on V2? So V2, now be careful, V2 is only for this part. Okay, so we know that there's I equals to V over R. I equals V over R. So if you had to get the V by itself, then you should end up with V equals to I multiplied by R, right? You've probably seen my triangles that I've made here. So remember, when you're looking for V, then you multiply these two at the bottom, okay? And so that'll be equal to, now, remember the current in A1 is 1.88 amps. So there's 1.88 amps go over here. So that's 1.88, 1.88, 1.88. When it gets over here, all of it goes through here, 1.88 amps. When it gets over here, some of it will go that way, some of it will go that way, and some of it will go that way. But the point that I'm trying to make is that this 1.88 amps is the main circuit current, and so that is the amount of current that will also flow through this resistor over here. So when we're doing this calculation, we can use 1.88 and we can use the 2.67, and if we do that, we end up with 5.02 volts. 5.02 volts. Then this one says, determine the magnitude of the charge, now charge is Q, that flows through A1 in 6 minutes. So they've got time and charge, so we should remember this formula or this triangle. Remember, there's the IQT formula or triangle. So if we're looking for charge, then charge is equal to current multiplied by time. So we know going through A1, we know the current is 1.88. So 1.88. The time is 6 minutes, but we definitely want that to be in seconds. So we multiply that by 60. And so if you had to work this out, you end up with 6, where did I write that? 676.8. And charge is measured in Coulomb.